Okay, this is 5.4, and today we're going to look at special cases within systems of linear equations. And really, special cases just goes back to what we were doing when we were solving equations. Sometimes when we're solving an equation, our variable would disappear. So if I had 2x minus 5 is equal to, let's say, 2x plus 3, doesn't really matter. When we subtracted 2x from both sides, we were left with a statement negative 5 is equal to 3. We said that was not a true statement. Negative 5 does not equal 3, and this was no solution. But let's say I change, and I'll just do it again, 3x minus 5 is equal to 3x, we'll just say minus 5, and I get the same on both sides, or if I was subtracting 3x, and my variable disappears, and I get a true statement, that was infinitely many solutions, all real numbers. There isn't a number that I could plug in for x that's not going to give me a true statement, and that's what we're going to look at with systems. So our directions here, solve by substitution or elimination. I mean, when I look at this right here, absolutely, I think to myself, it lines up nicely for elimination. Everything's lined up. I've got like terms oriented with like terms in a column because I'm going to add these down. And I also like to notice that I have coefficients that are the same. One is positive, one is negative, so my y's will eliminate. 4x is equal to 12. I would divide by 4. X then is equal to, well, actually that is a negative 12. So x is equal to a negative 3. I will take that x, I'm going to substitute it in right there so I can solve for my y. 2y plus x. X is now negative 3, so 2y plus a negative 3 or 2y minus 3, however you want to look at it. I would add 3. 2y is equal to 6, divide by 2, and I get a y is equal to 3. I would have the ordered pair, negative 3, 3, as my solution. I can certainly check this. If x is negative 3, that would be negative 9 minus 6 is negative 15. I'm good. What I really want us to start looking at this, and the idea behind looking at these equations and thinking, are we going to get something with one solution, meaning are my lines going to intersect, and I'm going to get that ordered pair of that point that lies on both lines, or they could possibly be parallel, same slope, running next to each other, never intersecting, no solution. And in this case too, I could have two lines that have the exact same equation that would lie on top of each other. In that case, we would have infinitely many solutions. The ordered pair, any ordered pair that I plugged in is going to work in both equations because they're the same equations. So what I really want us to pay attention to here is look at this equation. If I solve this for y, you have the same coefficient here. If I move this 3x over and this x over and divide both equations by 2, I just want you to notice if I graph these, my slope is going to be different. And when your slope is different, you're always going to get a solution. You will get one solution because those lines will intersect. Even if the slopes are real close and they don't look like they do, and they don't look like they're going to intersect in a coordinate plane, they eventually will. Because the rise and the run are different, they will eventually run into each other. So we're going to look at this solved by graphing. And these are both solved for y. They're already in slope-intercept form. I have a slope of 3 in the first equation and a y-intercept, or a b of negative 2. My second equation, I have a slope of negative 1 and a b of 6. Now I can tell right now I have different slopes. One is 3, one is negative 1. When I graph these, they better intersect. They have different slopes. I'm going to plot -2. For my first equation, there's my y-intercept. I leave my pencil, a rise of 3, a run of 1 with positive slope. That line should be rising, and it is. I can also go down 3, which is a -3, to the left 1, which is a -1, which a negative divided by a negative is still a positive. So that slope is still positive on the back side. And I get this line right here, which is not drawn very accurately, so I will hit that again. I like that better. Just clean that up a little bit. And again, the accuracy is key on these because I'm looking for the exact intersection. A b of 6 and a slope of -1, falling line, down 1, over 1, and I get that intersection right there, which is terrific because that's what I want. There's my other line. The ordered pair, or my solution to this system, is to the right 2 and x of 2 and up 4. And I certainly can test that in both equations. 4 would have to equal 4 would have to equal 3 times 2, which is 6. 6 minus 2 is 4. 4 would be here. -2 plus 6 is 4. And I am going to notice when looking graphically as well, and in y equals mx plus b, the slope is different. You have one solution. Let's look at these next ones. We're still going to solve by substitution or elimination. This one lends itself nicely to substitution. And I'm going to actually do it both ways in this one. First thing I'm going to do, though, is look at elimination, because elimination is always going to be my go-to method. And I'm at least going to line these up, get like terms, x's with x's, y's with y's, and just take a look at it and see what it looks like, because manipulating this equation is really easy. This -3x, if it is over here, these would line up. So I'm just going to move this over here first. I'm going to rewrite both equations. I have y plus 3x is equal to -2, and I'm going to move that over by adding 3x to both sides. So this is y plus 3x is equal to 4. And hopefully you can see right now that if I moved that over and that over, these actually have the same slope. Lines with the same slope are parallel, they won't intersect. This is something that I'm going to get no solution for, but when I go by elimination, it's going to look a little different than it does graphically. It's not going to, the solution's going to be the same, but it's going to come out algebraically different. So I could subtract this equation, multiply by a -1 to get some variables to eliminate here. And that's exactly what I'm going to do. These were exactly the same. I multiply everything by a -1. My y's would eliminate, my x's would eliminate, leaving me with 0. And then -2 subtract 4 is -6. Does 0 equal -6? No. This is no solution. If I just went by substitution, I would take this -3x plus 4, plug it in right there. So y is now -3x plus 4 plus 3x is equal to -2. And I can see again, those are going to eliminate. Anytime I subtract something from itself, it's 0. My variable disappears, and I get a statement that is false. 4 does not equal -2, and it's no solution. So you're going to get the same way, and what we need to know, you're going to get the same answer whether you do elimination or substitution or you did graphically. These lines aren't going to intersect. But when I do it, substitution elimination wise, your variables may go away. They may disappear. When that happens, if it's false statement you're left with, 0 equals -6, 4 is equal to -2, then we have no solution. And again, if we look at this graphically, get them to look like y equals mx plus b, and hopefully you can see if I subtract 3 here from both sides, this equation now is y is equal to 2x minus 3. So I have y equals 2x minus 3, y is equal to 2x minus 1. I have a slope of 2, a b of negative 1. I have a slope of 2 and a b, or a y-intercept of negative 3, and I can see right now these lines are parallel. Slope is the same, y-intercepts are different, they are never going to intersect. I'll plot them. B of negative 1, y-intercept of negative 1, then a rise of 2, run of 1, and I'm going to carry that out, and then I will go down 2 and over 1 to take that on the back side. I'm going to connect those points. There's a line. And notice, now it's negative 3. And you are going to have a rise of 2, a run of 1. It's going to keep going up 2 and over 1 following this line. But notice, it's never going to get any closer because the slopes are the same. The y-intercepts are different, the slopes are the same. These lines are parallel, and they will not intersect. And again, just like what we did graphically before, I can graph these lines. They may look parallel, but the determining factor was looking at the slopes to prove it. Last one here, solve by substitution or elimination. I'm going to go through elimination first. If I have negative 10x minus 2y is equal to 4, I'm looking at it right here, and hey, if I move this 5x over using inverse operations, add 5x to both sides, so plus 5x, now I have a positive 5x plus y is equal to negative 2. I'm going to rewrite this equation here, this negative 10x minus 2y is equal to 4. And now I'm going to look, everything's lined up. No coefficients that are the same. I've got some opposite signs. I can see here if I multiply this top by 2, that'll get rid of my 10x's. And it also, if I'm looking real close, is going to get rid of my y's. 2 times 5x, 10x. 2 times positive y, positive 2y. 2 times negative 2, negative 4. Not negative 4, sorry, that's a positive 4. No, it's not. Excuse me, I was looking at the other equation. 10x, 2y, negative 4. Then I have negative 10x minus 2y is equal to positive 4. If I add down, eliminates, I am left with 0 equals 0. That is a true statement. And when that is true, it is infinitely many solutions. There's no ordered pair that's not going to work. And if I notice, if this equation, if I divided everything by 2, it's going to be the same as the other one. The variables disappear, and you're left with a true statement, infinitely many solutions. Those are the same lines. If I look at substitution, which this lends itself nicely for, I'd take this negative 5x plus 2 and put it in here for y. This equation is negative 10x minus 2 times y, but I'm going to use negative 5x minus 2 to represent y, and that will equal 4. Negative 10x, negative 2 times negative 5, positive 10x, negative 2 times negative 2, positive 4. Does that equal 4? And look what's going to happen here. Whether I went by substitution or elimination, those will go away. 4 is equal to 4. That is a true statement as well. That is infinitely many solutions. And again, what we want to notice, variables, they disappear. So your variables go away, just like they did with no solution, But this time you are left with a true statement. And those lines are exactly the same. This is infinitely many solutions. What's it look like graphically? And you could think of this one as if you were going to graph it. This is already in y equals mx plus b. This one, if I solve for y, I would just divide everything by 4. Y then would equal negative 1/2 x, because negative 2/4 reduces to negative 1/2, plus 8 over 4. 8 divided by 4 is 2. And if I notice, I have the exact same equation. It is the same line with a slope of negative 1/2 and a b, or a y-intercept of 2. I will plot my y-intercept of 2. Negative slope, it's going to fall down 1 to the right 2, or up 1 to the left 2. And I could keep going, carrying this out in both directions. That's plenty, because this is the same line. I'm certainly not going to graph it twice. But if I graph the other one, of course it would lie right on top of it, meaning any ordered pair that works in one is going to work in the other. That will always be the case because it's the exact same equation. And again, you have the same equation. And when that happens, infinitely many solutions. Any point that I want to check that lies on this line is also going to give me true for this one. They are one and the same, infinitely many solutions.